Simple plane regions, area of plane regions. So this is the third chapter of integral calculus. We are now entering the chapter which is about the applications of integral calculus. And these applications have to do with finding the area of a plane region and later on finding the volume of a solid in a three-dimensional space. Area of a plane region. Given a continuous function f of x on the interval ab where f of x is greater than or equal to 0 for all x in that interval, the area of the region bounded above by the curve, below by the horizontal axis from a to b is the definite integral. The area of that region a is equal to the integral of f of x dx from a to b. This is how I began talking about integration or integral calculus. I explained to you at the beginning of the semester two interpretations of the integral. We can look at it as the area of a plane region bounded by a function such as this one, okay? Or we can look at it as the antiderivative, which is why we have a chapter in integral calculus which is anti-differentiation. Anti-differentiation is like reverse engineering the results of differentiation. And so those two interpretations, the integral as the area of a plane region and the integral as the antiderivative, they are put together in one fundamental theorem of calculus, which we call the fundamental theorem of calculus. What are we doing when we are getting the area of a plane region that is bounded above by a function such as this? Well, this is what happens, okay? So what we did here, and this is how I explained it to you at the beginning of the semester, we produce a partition of the interval. The partition is like a subdivisions of your plane region, so that we are subdividing it into strips of rectangle from A to B. You begin from A and then you end on B. Now, what is the purpose of producing this partition? Well, if we want to estimate the area of this plane region, what we do is we get the area of each of these strips of rectangle. And it's easy to compute for the area of a rectangle, okay? So the area of a rectangle is just length times width. If our partition is a finite partition, our approximation is of course an approximation. So if we want to produce the exact area of that plane region, what we must do is we must produce a partition in such a way that n, the number of rectangular strips, goes to infinity. And when that happens, I hope that you can see here that our rectangular strips, because we are producing an infinite number of rectangular strips within this partition, our rectangular strips will appear like line segments, okay? Line segments. And we will compute for the area of each of those. They appear to us as line segments, but we began it as designing them to be rectangular strips. The polygons that we are inscribing into the plane region need not be a rectangle. It can be a trapezoid, for example, okay? A trapezoid, something like this. So in effect, we are just getting or summing up. We are summing up the areas of these rectangular strips as n goes to infinity. And this is how you write it, okay? It's the limit of the summation of f of x times delta x as n approaches infinity. Delta x, you can look at this as the base or the width of your rectangle. And this one is going to be the height of that rectangle. Now, if the limit exists, that is the area of this plane region. And if the limit exists, we write the summation in this way. It's the integral of f of x dx from a to b. How do we do definite integration? So we call this the definite integral. How do we do it? First, we get the antiderivative. And then we evaluate the antiderivative at the limits of integration. Now suppose our plane region is bounded by two curves. Both of them are continuous and both of them are above the horizontal axis. So given a region that is bounded by two functions, two continuous functions, f of x and g of x, in the interval AB, its area is given by this. So what is happening here is something like this. First, we get the area of the plane region that is bounded above by f. And using definite integral, that is just the integral of f of x dx from a to b. Then, we will get the area of the region that is bounded above by g of x, the red curve, okay? And that shaded region there, that blue, light blue shaded region, that is the area of the region which is represented by this, the integral of g of x dx from a to b. So what happens here, if we want to get the area of this region, this light orange plane region, what we do is we do the subtraction, okay? We will subtract this, the area of this plane region, the blue shaded region, we will subtract it from this one, and the result is this. This is the result. Now, if our functions are not above the x-axis or not above the horizontal axis, we will have to do some adjustments. Okay, so this way of integration is done when our functions are above the horizontal axis, which means they are positive. So if they are below, we must make some adjustments. And I will devote a separate recorded lecture on that. Set up the definite integral to get the area of the bounded plane regions. So suppose, for example, this is the plane region we are working on. What is the area of that region? That light blue or light violet region. It's bounded above by g of x and bounded below by the square of x minus 1. Okay. Well, first you must pay attention to what is the function that bounds the region above it. What is that function that sets the boundary above the plane region? Well, in this case, it's going to be g of x. And that is the same as the curve defined by y is equal to x plus 1. Next, you now pay attention to the curve that bounds the region below the region. Okay, what is that function? Well, in this case, it is the square of x minus 1. And that curve is this curve, okay? Y is equal to the square of x minus 1. So when you set up the integral, you locate the limits or the limit of integration. So in this case, okay, by inspection, and it's quite obvious that the boundary of integration or the interval of integration is going to be from 0, okay, so this is your A, 0 to B, okay, and B here happens to be 3. Okay, so sometimes the plane region will reveal to you right away, okay, the interval of integration, but it's not always the case. So the instructions here is to write, to set up the integral that will give us the area of this plane region. So it's going to be something like this. It's the integral of x plus 1 minus the square of x minus 1 dx evaluated from 0 to 3. How about this one? Set up the definite integral to get the area of the bounded plane region. So what is the area of that? So again, we pay attention to the function that bounds the plane region above the region, and that's going to be g of x is equal to x squared. No, it's not g of x is equal to x squared, I'm sorry. That function is the green curve. And that curve is the curve or the graph of this function. F of x is equal to negative 0.5 times x plus 3 times x minus 3. The function that bounds our plane region below the region is this one. Y is equal to x squared, okay? Now the question is this, what should be the interval of integration? Well, looking at it, the interval of integration is not easy to estimate because it is short. It is short of negative 2, and right here it is also short of x is equal to 2. So it's close to negative 2. Greater than negative 2, that's the value of a, and the value of b is going to be close to 2, approximately equal to 2, but less than 2. So in this case, the interval of integration is not obvious. And any guess? Any thoughts about how do we move forward with this integration? Well, you must identify what is the value of a and what is the value of b. And you can do that by looking for the points of intersection. Okay? What is the point of intersection of these two functions? And how do you get it? Well, you will solve. This is the definite integral, but we don't know a and b. So what we do is we solve a and b by solving this equation. Okay? Because at the points of intersection, g of x is equal to f of x. Solve for x. And you know how to proceed because this is a quadratic equation. But we will not do it here, okay? So my intention for this lecture is just to give you the general picture about how you do integration, the definite integral, when we are trying to get the area of plane regions that are bounded by curves. And so this is how you do it.